Welcome to our unit on electromagnetic induction. Now this is probably an unfamiliar topic to most people, but in the end what it's really about is how electricity is generated for our use in homes, in industry, wherever we need it. So in Manitoba, we produce hydroelectricity using hydroelectric generating stations. And those generating stations use a principle called electromagnetic induction in order to produce electricity. So that's really where we're going. That's what it's all about. And this is all about the process of generating electricity using this specific technique. Okay, but before we can actually get all the way there, we have to put a few building blocks in place. The first one is called magnetic flux. So before we get into what magnetic flux is, I want to remind you about a couple things. The first thing is from magnetic fields, well, both of these things are from magnetic fields, is our formula for magnetic force. That's the first thing. Remember, it's QVB sine theta, but let's ignore the sine theta part first. So this is all about charge, velocity, and field strength. So when a charge is moving through a magnetic field with a certain velocity, a force is produced on that charge. Okay, that's what that's all about. Now, if we're ignoring the sine theta part, we are then assuming that the velocity and the field are perpendicular to each other. Okay, but often they're not, right? And that's why we have the sine theta thing in there. It's not that you always used sine theta for the angle that you were given. It's signifying to you that you need to use the perpendicular component of either the velocity or the field in order to get the correct amount of force that that charge is going to experience. Okay, so that's the first part. We need to remember that the velocity and the field are perpendicular to each other, and that produces a force, or we need to use the perpendicular component of one of them to get the full force. The second thing that we need to remember is how magnetic field lines work, right? So I'm going to draw you a little bar magnet here. Here's our north pole and our south pole. Magnetic field lines are drawn from north to south outside the magnet. And we have to specify outside the magnet because there is an object called a solenoid, or solenoid, depends where you're from, how you say that word. I'm going to say it's solenoid. There's an object called a solenoid that has an inside to it, right? It's this thing. So with this thing, when you run electricity through it, you run a current through the wires, it produces a magnetic field, right? And we use our right hand rule like this. So let's say I'm running electricity through the wires in this direction. That would mean that I use my fingers like this. My thumb points in the direction of the magnetic field inside the loops, right? So in this case, this bar magnet that I've drawn, I have to specify that the field points from north to south outside the magnet because it's actually the opposite inside the magnet, in there. Okay, so we need to remember what a magnetic field looks like because that's going to make a difference for flux as well. So here's the situation. Magnetic flux is the density of field lines through some sort of surface. Okay, that's a little bit strange to think of field lines going through a surface because we haven't really talked about that sort of thing. It's always been field lines in a loop of wire or field lines in the open air or something like that. And in this case, we are again going to be specifically talking about field lines going through a loop of wire. Okay, so here's my whole set of loops. There's the opening. And magnetic flux is how much magnetic field is passing through that opening. Okay, so this loop of wire, this is the surface that we're talking about. So magnetic flux depends on how strong the field is that's being applied, where it is, that really where the magnet is, that affects the strength of the field through that surface over there. So if I have this magnet far away, like this, then it's not going to be very strong over here, right? But if I put the magnet all the way inside that coil, then I get a much stronger field there. Okay, and that's what magnetic flux is measuring. It's how much field, what's the strength of the field inside a certain surface. And in this case, the surface is a coil of wire. And so the magnetic flux depends on these two things: the field strength inside the coil and the area of the coil itself. So here's our formula. Magnetic flux, you can draw this a number of ways. It depends on what font you're using, equals BA, where B is the magnetic field strength and A is the area of the coil. Okay, so this is the field strength, and that will be in Teslas. And A over here, this is the area of the coil, and that needs to be in square meters. Okay, and this thing over here, this Greek letter phi, this is magnetic flux. It is measured in Webers. Okay, I'll write that word over here. Nope, not Werbs. Webers. There you go. Okay, so Webers is a named unit. If we quickly take a look at what its base unit would be, field strength is Teslas, area is square meters, so that's Tesla meters squared. Teslas is newtons per amp meter times square meters. So that would give us newtons, or Newton meters per amp. So that's sort of the base unit. It's really not very useful to know what the base unit is, though, right? We could simplify. We could expand this even more by expanding newtons into its base unit, kilogram meters per second squared, and by expanding amps into coulombs per second, it gets a little bit crazy there. But just, it's not a useful unit really to visualize what's going on, so we are exclusively going to stick with Webers. Okay, let's try an example. If the magnetic field strength is 2 Teslas and a square loop with a side of 2 meters is inside the field, what is the magnetic flux in the loop? Okay, so this is an area of field that has a loop inside it. Okay, so we're trying to figure out what the magnetic flux is. Magnetic flux is the field strength times the area. Now in this case, this question does not tell you the area of the loop, right? What it tells you is the shape of the loop and its dimensions. So this is a square loop, and we should remember that the area of a square is length times length, right? Or length times width, but the length and width are the same in a square, right? So this is length squared. That's the area of a square. So whenever you're figuring out the flux through a loop, you need to know what type of shape it is, and you need to input the formula for the area of that shape into the area spot. It's not often that when you're just figuring out the flux, it will tell you the area of the shape, but sometimes it will. Okay, so now we have flux is equal to the field strength, which is 2 Teslas, times the area of this square loop, which is 2 meters by 2 meters, so that's 2 meters squared, not 2 square meters, but 2 meters squared. Hopefully that makes sense. So then our flux is 2 times 4, which is 8 Webers. It's not a vector, so it has no direction attached to it. It just gives you an idea of how much field there is. I don't know how else to describe that. How much field there is in this area. Okay, now the maximum flux will occur when the plane of the loop and the magnetic field are perpendicular to each other. And let me draw you a diagram to show how that works. This is an area of magnetic field, pointing to our right. Then we're going to insert a loop of wire into this field and show what kind of area of field we get, what the flux would be. So let's say, first of all, let's start off with, we have a loop like this. I don't know if the perspective makes sense to you here, but this loop is oriented perpendicular to the field, so that all of these field lines are passing through that loop. Okay, hopefully that makes sense. Drawing 3D is not easy all the time, especially for me. Okay, now let's say that we tilt that loop, so now it's no longer perpendicular to the field, now it's going to be at some angle to the field, 45 degrees-ish. Okay, so then we get something that looks like this. Okay, there's our new loop. Now you can tell that less field is going through that loop now, right? When you tilt it, you just get less of that area that's actually available to the field to go through. And then if we would tilt it even more, so we started like this, now we're like this, if we tilt it all the way like this, okay, there's our loop. Perfectly parallel to the field. When the loop is parallel to the field, we get no flux, right? Because there's no amount of field that's actually going through the loop. So here's our situation. Here we have our field is perpendicular to the area, or perpendicular to the plane of our loop, and so you get the maximum amount of flux. Here we have B and A. They're not perpendicular, but they're also not parallel to each other. And so you just get some flux, just less flux than you did when they were perpendicular to each other. And in the final one, you have your field is parallel to the area, or to the plane of the loop. That's really what we're talking about. Then you get no flux. Okay, so the formula that we used before, this one over here, flux is equal to the field times the area. That's true, but that's only true when B is perpendicular to A. Okay, that's important. So before, when we figured out force on a charge moving through a magnetic field, we needed the velocity and the field to be perpendicular to each other for the QVB formula to work. And when that wasn't the case, we attached a sine theta onto that thing to show that we needed to use the component of the velocity that was perpendicular to the field. And it's similar here. So we need to adjust our formula a little bit. And let me just draw a diagram for reference before we change our formula. So here is our loop. Okay, you're looking at the edge of it. If you want the 3D version, it's going off this way, behind us. There's our loop like that, but you're looking at the edge of the loop. Okay, now this loop, it's important when we take measurements that we use a normal line. Remember normal lines from way back in waves in grade 11? A normal line is just a 90-degree line, a 90-degree reference line to the loop that we're talking about, or to the plane that we're talking about. So in this case, here's our normal line. It just gives us a reference for what's perpendicular to the loop. Now, we are going to put in a magnetic field. Here's our magnetic field vector. It's right there. That's B for field. Now, this no longer works to figure out the amount of flux by using just B times A, right? Because we have to modify the amount of B that we're actually using, because not all of it is actually going straight through the loop. Okay, and so here's what we're going to do. We need to measure the angle between the field and the normal line. This is the theta that we're going to use to figure out how much different is our field from perpendicular. From perfectly perpendicular, we just use flux equals BA, but if the field is not perfectly perpendicular to that loop, then we have to use components again. Okay, and so our components would look something like this. if I split my field vector into components, I would have a parallel component and a perpendicular component. Now I said parallel and perpendicular in what seems to be a strange place, but I was talking about with reference to the normal line. Okay, and again, because we're measuring our angle from the normal line, this right over here would be B parallel to the normal line, and this over here would be B perpendicular to the normal line. It isn't really necessary that we use those two variables, that we name them that way, because we're going to make sure that the angle that we're using is between the normal line and the field. Okay? So we want to use B perpendicular in this case, or sorry, B parallel to the normal line. And what that means is it's the adjacent side of this triangle, right? It's the adjacent side of the triangle, and that means we need to use cosine. So all along we've been using sine for all of these, figuring out the component that we need, but because this particular formula, we're using the angle between the normal line and the field, then we need to use the adjacent side instead, which is cosine. And so here's the version of the formula that we're going to use. But you just have to be careful which angle you're given and which one you're putting into your formula. So flux is equal to BA cosine theta, when that theta is between the normal line and the field. Okay, let me write that down here quickly. Between B and the normal. That's important. So it's a very good idea when you're solving a problem to first of all draw it out. Just a quick sketch to show where the angle is that you've been given and where the plane of the loop is, where the normal line is, and where the field is. And that will help you make sure that you put the right angle into that formula. Okay, let's try this example here. What is the flux through a circular loop if the magnetic field the loop is in has a strength of 4.5 teslas and the wire loop has a radius of 1.1 meters? The loop makes an angle of 58 degrees from the normal to the wire loop to the magnetic field. Now that phrasing seems a little bit unclear, so I just want to highlight this last little bit. The loop makes an angle of 58 degrees from the normal to the wire loop to the magnetic field. So the normal to the wire loop just means that normal line that we were talking about. Okay, so let's draw ourselves a little diagram over here. We've got our wire loop, and I'm just going to make it horizontal. Well, I'm going to try to make it horizontal. I'm going to try that again. That's a bit better. So there's our wire loop. Again, we're looking at the edge of the wire loop. And there's a magnetic field in it. The wire loop is a circle in this case. The loop makes an angle of 58 degrees from the normal to the wire loop to the magnetic field. Okay, so here's our normal line, which is 90 degrees to the loop. And then from there, the field is 58 degrees. And it really doesn't matter what direction it is because the flux is not a vector anyway. It doesn't really matter what direction it is. So I'm just going to put it over here somewhere. There's our field. And so our angle is right over here. And it says that the angle we're given is 58 degrees. Okay, and it's 58 degrees between the normal and the magnetic field. That's what it's trying to say. So since that is the one that we're looking for, since the angle it gives us is the one that we want in the formula, then we can just use flux equals BA cosine theta. Okay? If instead, let's say, it had told you that the angle was 58 degrees between the plane of the loop and the field, then it would be telling you it was this angle, right? And that one does not fit in our formula. So then you would have to think for a second, okay, if it says 58 degrees is between the plane and the field, then I need to subtract that from 90. I need to use the complement in the formula. Okay, so it's going to take a little bit of thinking, so make sure that you're putting the right angle in there. And by right angle, I mean correct angle, not 90 degrees. Okay, in this case, it's a circular loop. So we're going to use b times pi r squared times the cosine of that angle. So that is 4.5 Teslas times pi times the radius is 1.1 meters, and we need to square that radius, and then we want to multiply that by the cosine of 58 degrees. Okay, no algebra required because it's asking us for the amount of flux there is, so we just need to multiply all those things, and you should get 9.1 Webers. So the version of the formula that we talked about previously only accounts for when the field and the plane of the loop that we're talking about are perpendicular to each other, right? So that very first thing that we drew, where you've got the loop and the field, which are perfectly perpendicular to each other, that's when you get flux equals BA, or the field times the area of the loop. But that's not nature, right? Not everything is always perpendicular to each other. So we need to make a second version of the formula that works always, right? So here's our situation that we find ourselves in. We're looking at the edge of the loop right here. So it's going off into the distance there. Here's our loop, but we're looking right at the edge of it. So we're going to draw a reference line on this loop called the normal line. Right there. So remember the normal force. The normal force is the support force that a surface exerts on an object. And it's always perpendicular to the surface. So if here's our surface, here's the normal force. Tilt the surface, and the normal force tilts as well, because the normal force means perpendicular. So this red line that I've drawn here is the perpendicular line to that loop. And that's going to be our reference line for all of our measurements. So now let's say that we have a magnetic field, and I'm just going to draw a single vector for that magnetic field. I'm going to draw it better than that. There we go. There's our magnetic field, B. So you can tell that our field and the plane of the loop are not perpendicular to each other. If they were perpendicular to each other, the field vector and the normal line would be parallel. They'd be right alongside each other. That would tell us then we could use flux equals BA. But in this case, the field is not perpendicular to the plane of the loop. It's not parallel to the normal. There's some sort of angle between those two things. Okay, and so here's the angle that we're talking about. This is how much the field is away from perpendicular. That is the angle we need to use. Okay, now if we talked about components here, let me use a different color. If we talked about which component we need to use of the field to be the correct component, we need the component that is perpendicular to the field. Or not perpendicular to the field. We need the component of the field that is perpendicular to the loop. Right? And so that's this one. We can call that B perpendicular. It's perpendicular to the loop. If you're talking about its direction with reference to the normal line, that would be B parallel, right? But the naming of it actually doesn't matter in this case, as long as you understand how this is working. So here is the parallel component, B parallel, and we want the component of the field that is along the normal line, right? That's perpendicular to the area, to the plane of the loop. So we want B perpendicular. Now that is the adjacent side of that little triangle that we just drew, right? That components triangle. Since it is the adjacent side, that means in this case, cosine is the trig function that we're going to use. Okay, so now we have to adjust our flux formula like this. Flux equals BA, which is true when the field and the plane of the loop are perpendicular. But since we need to use the component that is adjacent, or the adjacent component of our triangle, we're going to use cosine theta. Now, the thing that's important to remember here is that you can't just plug whatever angle you want willy-nilly into that spot. It has to be the angle between the normal line and the field. Between the normal line and the field. That's important. As long as you're putting that angle into that spot, you're going to get the right answer, because that will give you the correct component. If instead, let's say you took this angle over here, the angle between the loop and the field, and put it in there, then if we did some quick component drawing over here, you would want to use this component, because that's the component that's perpendicular to the loop, right? And in that case, it would be sine and not cosine that you'd be using. So it's important that if you're going to use cosine theta, you are using the component of the field that is along the normal line, right? And that means using the angle that is between the normal line and the field. Okay, let's try an example. What is the flux through a circular loop if the magnetic field the loop is in has a strength of 4.5 teslas? Okay, so that's the strength of the field. And the wire loop has a radius of 1.1 meters. So circular loop, so we'll need to remember that. The loop makes an angle of 58 degrees from the normal to the wire loop to the magnetic field. Okay, so that last sentence is kind of weird, and I'd really like to rephrase it one of these years, but not this one. So what it's just saying is that there's a 58 degree angle between the normal line and the field line. Okay, so here we go. It's generally a good idea to draw these things out to make sure that you are using the correct angle, but this one tells us in the question, the loop makes an angle of 58 degrees from the normal to the field line. So I know that the theta that we're given, that 58 degrees, is the one that goes in the formula. Okay, but I recommend that if it's not completely clear, if it's giving you compass directions for where the angles are, draw it out. That'll make sure that you put the correct angle in there. Okay, so BA cosine theta, that's what we're using. And so we're trying to figure out what the flux is. Don't need to reorganize anything then. B is 4.5 teslas. The area, it doesn't tell us the area, but it tells us the radius. And if you remember the formula for the area of a circle, it's pi times the radius squared, right? So we're going to go pi, times 1.1 squared, pi r squared, that's going to be the area that goes in the formula, times the cosine of 58 degrees. Okay. Okay, so using this formula is pretty straightforward. The two things that you have to keep in mind are, number one, you got to put the correct angle in there. So make sure that you're putting the correct angle in there. And number two, often it's not going to tell you the area of the loop. It'll give you dimensions of the loop somehow. And so you'll have to put the formula for the area of whatever shape that is into the flux formula. Okay, and so you should get, if all has gone well, 9.1 Webers. That is not a vector, and so you need no direction or anything. That's just telling you the strength of field, or the amount of field that's inside that wire loop.